as Abhishek mentioned, I've been leading the deep learning research there since 2013. We were lucky enough back in 2013, as the field was really just starting to emerge, at least from an industry side, to join up with one of the researchers who was still at Jeff Hinton's lab in Montreal. And we were able to work with him for about a year, and he really pushed us up the learning curve for the deep learning applications. And so that helped us gain quite a bit of momentum early on for these types of applications. And before I get into the slides themselves, I should mention these are other people whose work I will be speaking about today. So Edgar Bernal, Kishore Reddy, and Kingwin Lor are all people who have worked directly on the GAN models alongside with me. In general, we have a slightly larger team of people who are working in the deep learning area. And so the slides I'll be showing compared to the papers that you've already been looking at, it's going to be much higher level, no real math or results to dive into. And so just from kind of the intuition of what a generative adversarial model is you actually have two neural networks that are set in opposition to each other. One called the discriminator, which is simply going to determine if the information it's seeing is real data or something that was generated, which brings us to the generator, which is trying to learn how to, it's basically modeling your joint probability distribution. It's trying to learn how to generate data that's indistinguishable from real data it has seen in the past. These two are set in opposition to each other. They asymptotically level off in the end. The reason we're interested in the generative models, I mean, there are many reasons for it, but one of which is because it's modeling the full joint probability distribution. If it can do that well, not only can you then later use it for discriminative type of models, but you can also use it to generate data. Right? One of the people earlier was speaking about issues with when you have very few observable data points of the type you're interested in, right? You're kind of stuck. Under certain conditions, with a generative model, you can actually generate data that would normally be in the tails, right? And actually generate good outlier data, even, or at least supplement what you currently have. A couple of the notable properties of the GANs. The generator is a encoder-decoder model, what they call a UNet. And the main differentiator, I would say, between these types of networks and the typical encoder-decoders are what we call these skip connections. So hopefully you can see from the back, we've got the encoder and then a decoder, right? You can usually think of this as your bottleneck layer, but you see these additional connections that actually allow information to map directly from high frequency or the type of information. And what that allows the model to do is, especially the high frequency information, which is often lost in that encoding, if it's necessary to create, in the cases we'll be looking at, realistic images, then that information is able to be maintained by the model. The discriminator uses what's called the convolutional patch GAN. This image, I think, gives you a good intuition of what it's trying to do. It's actually sliding a patch, right, a window, convolving across the image, and at each position, determining whether it thinks that patch of the image is coming from a real data or from the generated data, right? It's basically saying, is this real? They also evaluate whether it's fake, right? The point here is that this particular, the discriminators use an L1 metric, which is actually better, again, at the high frequency data. It's better for replicating edges. But the final call on the discriminator is basically just a aggregation of how many of the patches it thinks came from real data versus not real data, right? So it just aggregates all these boxes here. That gives the metric for the discriminator, this piece of it gives it a bias towards local information, right? Small scale information and not the global picture, which is picked up by another facet of it. And I would say probably one of the most popular applications people have seen or have used, and many people immediately implemented in a number of interesting ways, is the work by Isla et al. Back in 2016 on image-to-image translation with the conditional adversarial networks. So what we were discussing over here on the original slide over here is just a generator, which is, so the generator is starting from a randomly sampled point. It's trying to generate an image. The discriminator is also seeing real data. It doesn't know which it's receiving. That's what it's trying to learn. And over time, as the discriminator gets better, information about how it got better is being propagated back through the generator. One of the nice properties, of course, is that the generator, which is trying to create pictures, never actually sees what a picture looks like, right? It's learning how to actually do that through a propagation of the weights from the detective model or the discriminator model. But when you're done with this model, what you're left with is a generator that you can just feed a random seed into, and it generates a picture, right? So that by itself is good for generating data, but it's not good for steering it to solve a problem that you're interested in. What the conditional GANs do is you actually are feeding it pairs of images, right? So in this case, you're feeding it, think of the data image from Google Maps, right? You can get the satellite image, and you can get the map itself. If you feed those in as pairs, you can train the model so that whenever it sees a map or a satellite image, it trains a map, outputs a map, or vice versa, right? So in this case, what you're doing is feeding in an image and a random seed and asking it to be able to map to the second image, okay? And these actually work surprisingly well. Here's an example of it mapping between very abstract representations of buildings and actually generating buildings. And of course, like I said, you can go backwards on any of these mappings. Sketches with the outlines of objects to real objects. And people did put a number of interesting applications online. If you haven't lost an hour playing with the Edges to Cats app yet online, I encourage you to do so, especially while you're away at a conference. But it's an application where they've trained on thousands of cat images, and because cat images paired with their outlines, and so they have an app online where then you can draw a cat, and it will map it to the best it can, a photorealistic version of a cat. Right? And of course, it only knows cats, so when you start drawing robots and monsters and all of those things, it still makes them look like cats. But so, again, I encourage you to do so. And so these slides will be available if you haven't already seen some of these online applications. So the point of what I'd like to discuss is even these applications, which as 2016 was when they originally came out, we started implementing them earlier this year, actually have some powerful applications to be used for PHM. And I'll speak about these three. There will be three. Originally I had five. I had to pull a couple back right before I left, but I'll give you a little bit of explanation. So multimodal learning, this is an old favorite data set of ours. It's a Ford driverless car data set that's available online. And it has registered video and LiDAR data. So you have depth data along with your video from a number of cameras. And in this particular case, what we're looking at are to make use of this image-to-image mapping to see if we could rig it to basically, you put in RGB images and LiDAR data as your pairs and learn the mapping so that you see how good of a LiDAR signal we could get only from image data and other types of data. We have super resolution was an obvious extension of the method. If you think of it, super resolution is, in this context, really just an image denoising method, right? And you'll see why in a minute. And the last one is multispectral encoding, and this is, we have a number of applications where we have multispectral images or hyperspectral images. For those of you who aren't that familiar with the difference, multispectral is usually fewer and, I guess, overlapping frequency windows, and hyperspectral usually have a large number of very specific channels for your images. So let's take a look first at the multimodal learning. This is in this particular case, what we were looking at was instead of just putting the RGB images in and then learning LiDAR, what else could we be putting into this methodology? So if we simply replace the RGB channels, in this particular case, the RGB channels are then replaced with a single black and white image, and then U and V, which are 2 dimensions of optical flow. Okay, that's why it looks so crazy, right? And see if we can use the image and optical flow to reconstruct the depth data from the LiDAR images. And as you can see, at least visually, this is reasonable. The other one was simply, it was an obvious extension, is to take a sequence of frames, say in this case 3, and replace RGB by 3 time steps of the video. If you look at the back wheels of the bus here, you'll see the same bus wheel as it drives by in red, green, and blue, right? And so this is really asking that same model to do structure from motion, right? It's getting a number of images and it's trying to create a depth map from that. So this is actually the actual flow of this is using whatever information we're putting into the model, constructing a conditional generative adversarial network to predict the depth information. And then actually taking this information, and what we do, we call it a cleanup model at the moment. But so the first step is actually doing the fusion to depth map, and then a second step which takes that output with the same target and tries to further improve it. Obviously, if you were to run it through that same model again, it doesn't actually improve it. But we found that this gives significant improvements by having 2 sequential GAN models to clean up the depth information.
Sorry, question.
Yeah.
The RGB, in fact, RGB are 3 different time slices?
So if you think of the RGB image, it's a 3-channel image. And if you replace red, green, and blue with a black and white image at 3 different time steps. So instead of putting R, G, and B in, we're just putting in 3 black and white time steps of the video. Okay.
So in principle, couldn't you also get depth just by doing serial triangulation?
stereo, yeah, but this is a single camera. Yeah.
Okay, I see.
And of course, it doesn't. With the driving data set, there are some pros to it. One of which is what it's seeing. There's a lot of consistency to what it sees. Some of the downsides are, especially in training this type of model, is you come to a light and you sit there, right? And so you have a lot of information when you're changing speeds, especially when you're taking corners and your camera is swinging faster than optical flow or this type of information can keep up with. One of the obvious things to improve this model is to account for those types of motions, but just driving straight down the street at a certain speed, it actually works fine. Yeah. I won't go into the too much into the results, but we can actually see improvements in the depth estimations from both the optical flow, but more so from multiple frames. The next application that we looked at was for super resolution. We have a number of super resolution applications. Of course, one of them that we're always interested in is being able to put cheaper, lower resolution sensors on things and still be able to get the same, or be able to create usable information from them. So whether that's enabling better low bandwidth video communications, you can imagine audio reconstruction, right, in the temporal domain rather than the physical domain. And so in this particular case, what you're looking at, again, with the same application basically, is I'm showing you in this image, removing every other row and column. So basically removing 3 of every 4 pixels in the image. By doing it that way, the information that you're leaving in there still has the spatial characteristics, right? It's still embedded in the original image space with the correct spatial information, and because of that, the convolutional neural net can take advantage of that. And so these are just a couple of examples, again with the Ford data set, where you're putting in, this is basically 4x reconstruction, this is what's output, and here's the actual target data. You can see the same for these. Right? This is actually 16-fold reconstruction, and these results are, you can, especially in these, you can start to see things falling apart a little bit. Right? One of the questions, though, in the work that we're doing is, it's one thing to reconstruct the image really well, right? But if the task that you're trying to perform is object detection, right? Then the question starts to become, how good does it need to reconstruct before you can use it for object detection, right? So it isn't always the visual reconstruction that you're necessarily aiming for, but the usefulness of that. So, as I mentioned, the one thing with the Ford data set that we learned kind of in reverse was that because of the consistency and the subject matter that it was seeing, right? So we've got cars and buildings on the side, cars in front, streets below you. It actually learned very strong models, and as you can tell, I mean, the 16-fold super resolution is, I would say, unreasonably good in this case. It's not always, but it is here. But I'll show you some examples later on more difficult data sets where things aren't quite that good. So again, what we're looking at here are reconstructions at different resolutions across the top. Top row are the inputs. I think you can just barely see the car and the parking lot in this image, and then as you have fewer and fewer pixels, right, you get less and less. You can kind of see the reconstruction. One of the things that you notice is the colors start to move towards gray as you get lower and lower resolution. We've seen this in other methods that have been used for super resolution, and there are actually ways of addressing that to a certain degree. I've seen these pictures on my computer at much higher resolution. I don't know where in the training set it learned to do this, but this looks extremely like a small dog or cat. It turned just some random point of the paint on the line into what looks like a small animal with a shadow next to it. Right? Just as a reminder that it can only say what it has seen, right? It can't always get things. And again, going back to what I had said earlier, then if we apply a secondary cleanup version to it, so here you're going from low res to high res, and then if we train a separate model where the inputs are the outputs of this, so that second row is the inputs to the second GAN with the same targets, you can hopefully see there that it actually does actually improve the outputs, especially in terms of cleaning up the edges, and you can see, especially if you look at some of these really blurry lines, or it will take information like that and try to sharpen it as much as possible. This is kind of the, showing you some of the warts that also get, when we move this over to where we're training on the ImageNet data set, and just a relatively small sample, right? So we pulled 13,000 images, so 13 images from each of the 1,000 classes. Obviously, the diversity of those images is much greater than the driving data. And in that particular case here, we're just looking at the 4x reconstruction. Even there, these images, the reason we have the asterisk next to them is because they were input similar to the slides before, right, with the missing rows and columns. Here, I just pixelated them to the correct resolution. This is a pretty low res image already. You can actually see the seams aren't realistic in these images. But when it tries to reconstruct it, we end up with these patches. Right? We actually end up with some pretty bad artifacts. You can see it when you're standing this close. We have some of the same thing around the edges of the shadows. So there are certain places that are very challenging for it. This particular image down here was a funny one where, because we were removing rows and columns, right, straight vertical and horizontal lines, what actually happened is the white edges around this box here got masked. So even though it tried to reconstruct the image, it had never seen that there was an edge on this lower image, right? And so when it reconstructed it without those edges. So these are from, just by the way, if anyone's interested, this BSD 100 data set that people use for super resolution experiments. I would just say, some of the other nice characteristics here. If you look at the seams on the reconstructed ball here, you actually see it was actually able to make good sense of them and actually, create pretty smooth continuity there. On the tennis image with the pixelation, you can see especially how poor the lines are with these methods, and again, it cleans edges up very nicely. For those who are interested, this work we currently just wrapped up all the evaluations to the external data sets. It'll be out shortly. And the last example, just wanted to speak about a bit, is on what we call multispectral encoding. And so in this case, what we're doing there's an example of taking RGB images and transferring those and mapping those to multispectral images, or taking low-res to high-res multispectral images. So you may have just a few spectral bands in your image, and you want to take it to a much higher number of spectral bands. An example of this, may be that you have, we'll say some limited sensor in terms of observation, but you actually need like a hyperspectral image, right? And so you need to be able to estimate more sharply across the number of bands for some application. If you think about it, this is really the same problem as the super resolution, right? All we're really doing is we're doing the super resolution, but in the spectral domain rather than the spatial domain. And just a couple of the results from this work, just again visually. In this case, we're just taking an RGB image, right? So 3 input bands, or spectral bands, which are pretty loose, and splitting it out, actually, trying to remember how many, I think this was split out into 31 spectral bands, and this is just a sample of the 31 spectral bands. But you can, if you look at the error curves down here, green being no error, right, and the blue are positive errors, you can actually see that it has done, at least just looking at it visually, has actually done a good job at separating out the spectral bands. This is not surprising, right? Trying to go from RGB to 31 bands, the error actually gets pretty bad because you're trying to bridge too much of a gap in terms of parsing the spectral information. But as you go from 6 bands to 31 or 11 to 31, or as the number of bins in your 2 spectral images gets closer and closer, the results kind of group together pretty quickly. So one? Really? I have one more slide. So this is usually where people say, what next? And given the pace of this field, I just say, what now at this point? Because a month from now, it'll be something new. Where we're, the GANs, in general, they call it the GAN zoo. There's a new one every single week in terms of the number of applications for them. If 2 GANs is good, or if 2 networks tied together is good, then 4 to 8 is even better. And so one of the obvious things are people are coupling these networks together in larger and larger groups of these of networks. 2 recent examples is disco GANs and the cycle GANs, and we actually see this as being one of the most important trends, really, to finally be coming to fruition for us, right? This is actually showing the promise of large-scale, unsupervised learning, right? Where we can actually free up human resources from doing every comparison between data sets that we think may have mutual information in them, and start being able to automate much of this, basically allowing the learning algorithms to find these technical nuggets, right, behind the scenes in some sort of an automated fashion. And anyway, we see this as really one of the most important developments that, on top of what already was with the adversarial networks. I'm out of time. All right, I will go. I was going to describe a bit more about what these networks were. Obviously, we can look them up offline, or I'm happy to discuss any of this work afterwards. I guess I'll leave it there then. That's it.
Thank you.
Sure.